Hello and welcome to Game Development for SDL and OpenGL. My name is Nate Nutzler and this is for Hyperactive Studios. Now we left off before with the keyboard presses and how we're going to set up to make things rotate and the draw scene in the cube. Now I went ahead and added in the zoom aspect for the right mouse button. So if I go ahead and run this application and I go ahead and I hit my right mouse button and I zoom in and out, and of course I can rotate my cube too in addition to that. So very cool and allows for a little extra functionality, and it's just nice to be able to zoom too. So that way you're not just stuck there. Alright, anyways, I'll get into how to do that. It's fairly simple. And we're just going to go over the main function now. And this is all that's involved right here. Okay, so we have our int main here. Open parentheses int argc, comma, char double not pound sign but stars argv here, close parentheses. Okay, so what is this? This is the number of arguments that are getting passed in to our program, and this is the argument list as a double pointer system. So this is a pointer within a pointer setup. Think of it as an array. If you're familiar with arrays, this would be like a two-dimensional array, but instead we're pointing to a two-dimensional array of memory address locations in RAM. So it's about the best way to explain it. And basically we can access these different these different arguments as a list of arguments in RAM. So whatever they typed in for a number of characters, that would be one array, and then the second array is the actual listing of each different character array. Basically, it's getting passed in as a double pointer list, if you will. Alright, and of course our return type here is int, so that way we know if it's 0, no problems at all. If there is a number, then it means there's some kind of error, and we can notify us of that error here. So open curly brace here, and that's exactly what we're getting into with these exit numbers here. We can get into defining a return value of something other than 0, then we know that we've had a unsuccessful execution of the program and that it crashed at some point in time. Alright, so if open parentheses SDL underscore init here, open parentheses SDL underscore init underscore video, close parentheses. So what are we doing? We are launching an SDL subsystem. In this case, the video. The video is a fancy way of saying basically displaying the graphics to the screen. That's another name for video. We're not talking about actually streaming a video or doing like a webcast or anything like that. You can do that with SDL with some additional extension libraries and such that have been put out, like FFmpeg for instance. But that's not what this one's referring to. This video here that we're talking about is actually displaying graphics to the screen. For instance, like you're playing a game, or in this case we're actually just rendering our graphics from our 3D cube and displaying them to the screen in the window. And that's what they're talking about video. They're meaning more like video card, not so much you're watching a video. So because of that, we got a particular setup here. Anything less than 0 here for this is an error, basically. So anything less than 0 here is going to be an error, and that's why we have the less than 0 part for this subsystem for the video here, close parentheses. And that's exactly what we have going on here. Open curly brace here. Comment here, we're just saying it's an error. It is an error. This is an error with the video subsystem. That's important to note here. We're not saying that there's a problem with all of SDL. We're just saying just with the video subsystem. So maybe there's some kind of problem with the driver for the 3D card or for your video card, or maybe there's something wrong somewhere in there. I don't know. Something's gone wrong. Something's happened. So we got a problem. So we're going to fprintf here. Open parentheses stderr. Here's a standard error file. This is used amongst lots of programmers, and this is typical for the name for the error file. Comma. Now fprintf takes basically from the C method of displaying to the screen with printf. When we say fprintf, we're actually going to create a file instead. So instead of being directed to the screen and being displayed on the screen, instead rather it's going to go to a file. So here we're going to say unable to initialize SDL, and then here we can say what the SDL error is. Unable to initialize video, maybe subsystem of SDLs, something like that, possibly. Might be more desirable. And then we'd have our error here. Exit, open parentheses, 1, close parentheses, semicolon. Close curly brace. Let's go over to our next one here. Okay, so here after the initialization of the SDL, let's talk about this part right here, which is our whole video set. And I went through the trouble of actually writing out all the possible options for it. I was just going to go on and say what this does, and then decided, no, let's give out all the options because that's be thorough. And that's what I've done here. So the first option here is going to be the window width, of course. The second one is the window height. This one is our bits of our color for our display. So like 32-bit, 24-bit color, 16-bit color, etc., etc., etc. We can set it to different values. If you're in window mode, you need to be setting this to 0 though, and not to some 16-bit, 24-bit, or 32-bit, because it's going to be using whatever the color bit is from the actual system it's currently running. However, if you're in full screen mode, you need to tell it what the color bit rate is going to be, what color bit mode you're going to go to, because that's going to make a difference for the way it's going to look on the screen. And then, yeah, it's just going to draw it in 16-bit, 24-bit, 32-bit, etc. And then here the SDL_OpenGL. Now this can be ORed. So for instance, say I wanted this to be like this, and then also wanted to be in full screen mode. I could do that. I could sit here and say OR here, and I could say SDL underscore full screen, for instance. I could do that, and then it'd be running in OpenGL mode and be full screen and take up the entire window. Okay, cool. And take up the entire display, if you will. And so you could do that. If anyone added another option to that, I don't know. Maybe you want to be, SDL double buffering, for instance. Double buff is going to be what you're going to put there. You could do that too. But in our case, we're just going to get away with just using SDL_OpenGL. Okay. If we want to make the window resizable, for instance, if I want to do this option here, which I can, if I like, I can now make the window resizable. And that would work there. There's more than that though. There's also OpenGL Blit, where in this case we're going to have we're going to work with OpenGL, but we're going to do SDL to do the actual rendering to the screen. I don't think that's really a good idea. I think you're better off rendering to the screen with OpenGL, because OpenGL is going to be 3D hardware accelerated, so you're going to get a faster performance from OpenGL, I would suspect. SDL_NoFrame here. That's going to be, okay, see how we have like these, okay, if I run this real quick. Alright, see how we have these window edges here or whatever? If I ran that with no frame, I would not have those window edges. So, very cool indeed. And you can see here we can actually resize our window now that we've, set it to where it can be resizable. So, very cool, and that allows resizing. Alright? Because before that, we couldn't resize the window. Just as a real quick, show you what I mean by SDL no frame, but that's what full screen runs in, is SDL no frame. Like that. So you can see here, there's literally no edges to this window. There was nothing there to work with. And you may want that. What if you're doing like a quad view CAD layout program or something like that, and you're drawing this as multiple windows within the side of the overall screen display? Hey, maybe that makes sense to do that then, with no border edges. So that could be a good thing. Totally up to you what it is you're doing or what you need. That's depending on what you want to do with that. And then we have SDL_any format. Sets you up to use the pixel format of the physical display device, your screen basically. Yeah, your monitor here. SDL_asynchronous blit. does asynchronous blitting. I think it's blitting, not blighting. Anyways, SDL underscore HW palette, 8-bit graphics from like the old Mario Brothers. Yeah, this is like if you want to simulate, I guess, if you want to make a game that looked like the old NES or, you know, Nintendo system, basically, is what I'm saying, or the old Sega Master System before Sega Genesis. Yeah, if you want to do, you know, one of those really old systems like the original Mario Brothers, then yeah, you could make one with that, and this would be a really fast method of drawing that. Modern day graphics have gone way past this. If you made a game like that, I don't think you'd do well too. Probably won't do too well in the market. But hey, it's possible. Here it is. This is how you do it. I'm not going to go over hardware palettes because I think they've pretty much bit the dust as far as I'm concerned from a game development standpoint. SDL underscore SW surface. Now, what this does is allows us to render our graphics directly in software. In our main memory of our RAM, and not on the not on the 3D card or video card or whatever you may have for video rendering. This is going to be slower if you do this, definitely. 3D cards are designed to render graphics and can handle, well, nowadays ones can handle trillions of threads at once, you know, so they can handle, you know, massive resolutions of pixels and compute them very quickly. So if you sit there and pass it over to a CPU, it's not designed to handle that. The memory architecture is not set up for it. The number of cores to be used to compute it aren't set up for that. So it's not really a good idea, but you can do it if you like. And then of course there's SDL underscore HW surface, which renders the display in hardware mode in the video card's memory, which basically lets us use the video card. Now in our case we're using OpenGL, so we really don't have to worry about that. And the only thing I added just now was making SDL underscore resizable here so that we can resize our window. Alright, if there's an error, I'm going to do fprintf. Okay, yeah, and if it's equivalent to null, if it returns null, that means we have an error. Something went wrong. It should not return null. Okay, so fprintf here, if it's returned null, standard error file again, and we're going to add to that file. Unable to create OpenGL scene, you know, SDL get error. So, you know, basically this has where we couldn't do SDL with OpenGL and resizable window. So, you know, create OpenGL scene, I would say with SDL. Let's be a little bit more descriptive. Okay. And exit status 2. Close curly brace here. Let's move on. initgl open parentheses window width, comma, window height, close parentheses, semicolon. And that basically just gets us set up with having OpenGL to display inside of our newly created window from SDL. So here we are, we have our window and there's nothing in there from SDL. That's all we got is a window. Great. Now we need to actually initialize OpenGL to draw inside of that window. So that way when OpenGL draws, okay, you know, so say you got your window. Here, let me go ahead and execute this thing. Okay, so say we got our window, it'd be nothing but, say, black, for instance, you know, sitting inside our window, nothing there, right? And then we're going to tell OpenGL, go ahead and define out your drawing area space within this window space completely. So then OpenGL is going to take up this entire space of this window to draw, okay, its window. And we set ours to match exactly the same size of the window as what SDL created. So therefore, for OpenGL. So therefore, when we initialize the OpenGL here, we're going to be eating up the entire space of that window. And that's exactly what we're doing there. Okay? And that was up here earlier in our init here with established projection matrix, width and height, you know, and that was setting up that size to fit within that window. And how we're going to draw, what our clear color is, so now it makes it black, etc., etc., etc. We're going to be doing our depth tests and all that stuff. Okay, cool. All right. And let's change this real quick to true. I'm going to say bool for this. I prefer that method. Okay, the starting value here would have to be false. Alright. So while not false, we make it true. We're just going to make it execute, right? So while not done, continue to execute. Okay, open curly brace here, draw scene, open close parentheses, semicolon, SDL underscore event, space event, semicolon, and then while here, we're going to do space here, open parentheses, SDL. Okay, so what are we doing here? First off, we need this is our game loop, if you will. This is going to keep repeating over and over again, looping, until we're done with the game. Once we're done with the game, the whole application closes, so that makes sense. Draw scene here. Now that's where we're going to use it to draw our scene. In this case, the cube. Alright, because in draw scene here, we cleared our color buffer bit, our depth bit. Here we set our GL matrix mode to our model view matrix. We loaded in our identity matrix as before. We did our translations for our moving back the cube and such, and then we're drawing our cube, and we're doing a GL flush to display those graphics, and then we're doing the swap buffers for our double buffering. Okay. And over here, if we do, and that's what our draw scene is, of course. SDL event, it's a special data type inside of SDL, and we're going to create the variable called event, so that way we can test our event within our loop here for our polling loop. So we're going to poll our different events, so that way we keep checking our events. There's 3 different ways to do this. There is the wait method, which I really haven't gone into here. I might show it a little bit later. The wait method is how most applications are actually written out there. It's also the most inefficient and poorly way. It's the worst way to do it. Okay, it's not what you want to do type thing. The wait method is that we wait for someone to click or do something in the application, and then once they do that, we go off and process whatever they clicked on. And then once we're done processing all that stuff, then we can come back to taking user input again. Downside to this is, you can't, you're executing wait like most of the time. 99% of the time, the application just waits. The other problem with this is once you do tell it to go do something from a click aspect or whatever, then if this is a long involved process, it's going to be quite a bit of time before it comes back to where it will take input from the user again to click on the next thing. And this is when people tend to think maybe the application's locked up, maybe something like that. So you're best off having something like a polling event and then executing it off as a separate thread or something like that nature in the background to take care of some event while you then read in other input for other things to be accomplished by the user. So makes sense to do that. The reason why it works for most applications, though, are most applications don't do computationally intensive tasks. So it makes sense to use that method because it doesn't. It's simpler and easier to set up. So, from a coding standpoint, it's simpler. Good example of why you would not want to use this wait method for a game, which the reason why I haven't coded it up in that method, is that say you have the wait method, like I said, you're waiting for someone to click or do something. It means all animation and backgrounds, animations, sound, or whatever's going to come to a halt while you're waiting for someone to click and do something else. So that's not going to be good, and that's not going to be useful to you. So in our case, we're going to want things going on in the background while we're doing stuff in the foreground too. So the polling event system or direct access to our peripherals like our mouse or keyboard or joystick or gamepad controller or whatever makes a lot more sense, and that's what we're going to use and do in these next set of videos. So right now it's a polling event system. It's cool, it's good. Later on I'll show you the direct access method, which is my favorite, but for right now we're just going to do the polling event system. Alright, so we're going to say why poll event, and we're going to say open close parentheses and event here, so we pass the memory address to our event variable, and this makes things go faster. Open curly brace here, and we'll say which here. We like to use a which statement to help make things easier and faster here. So open parentheses, event.type here, close parentheses. Open curly brace, case, space, SDL underscore key down, colon. So this detects was a key pressed. If it was key was pressed, then there's a key that's down. Then we can check to see what key was pressed from there. So if here open parentheses event.key. Now this is a key. This is important. We have to say dot key here. Dot key sim. All right, now we can get to our key symbol. Dot sim here from this data type approach here equals SDLK underscore escape. This lets us do the escape key on the keyboard. Now actual keys are going to be SDLK, K for key or keyboard. Underscore and then what key it is on the keyboard. In this case it's underscore escape. And here we can see done equals true. And I had set up done to be true false and then totally forgot to set the data type up there earlier and had it set to int. My mistake. Okay, so break here, semicolon. And then case here, space SDL underscore, and we want to do a break afterwards. Okay, let me point that out too. And by saying done here, we're saying true to done. So it's no longer not done becomes false, of course, because opposite of true is false. So if you say not true, it's false. There you go. So that, of course, means to stop looping, which means the game is over. So if someone hits the escape key, it exits our game here. In this case, the cube. Okay, so case here, space SDL underscore mouse button up here. So mouse button comes up. What we do here. So it's going to be / button space released. And this is going to be letting you, we're saying that we're releasing our mouse button. So if open parentheses event dot button I know that sounds crazy, but that's what it is. It's event dot button here, and this being our mouse buttons. And then what thing from the button we want to do? We want to do the actual button itself. So we're going to say we're going to test to see what button it is that was actually let go. And if this button happens to be button 1, then that's going to be the left mouse button. In which case, we want our left mouse button pressed equals false, semicolon. If open parentheses event dot button equals 3 here, close parentheses, then this is going to be our right mouse button. 2 is going to be our middle mouse button. So hopefully this makes sense here. So 1's going to be left button, 2 is going to be your middle mouse button, and then 3 is going to be your right mouse button. So we're going to say right mouse button pressed equals false, semicolon. Okay. / here, we're going to say report the event here. We're going to say fprintf here, open parentheses, standard out, comma, quotes here, mouse button %d here for a value here for what number it is, released, / n here, in quotes, comma, event dot button close parentheses, semicolon. So what does this mean? This is going to display this message and tell us which button, 1, 2, or 3 was pressed. In this case, left, right, or left, middle, right. So you know which button was pressed. And that's all getting kicked out to a it's all getting kicked out to a standard out file. Let's see here. It would be in keyboard, key mouse. This one right here, I think. Alright, and then there might be an executable for debug. Okay, I thought it was that one. Which one are we running here as? We're doing key mouse OpenGL. Okay, key mouse OpenGL. Key mouse OpenGL bin. Okay. Okay, so there we go. And then we can see right here in our standard out, when we run that program, we can see that mouse button 3 here pressed at, and then it gives us the location of where that button was pressed in the screen space here. And then mouse button 3 was released, so let's know that, hey, they let go of the mouse button. Here's mouse button 1 being pressed, and its location on the window where it was pressed. So this lets you identify where something is, so you can click it on some item on the window. It could be an enemy, it could be some menu item, it could be anything, right? Mouse button 2 pressed at, and then here we go to different mouse 2. You can press 2. So I pressed them all. Okay. And there's a really quick way, which is cool, of doing basically like a select all here, Control A, and I can just say delete and then Control S to save. And if I close this window now, it'll clear out this cache and this will basically clear out all the stuff in this file here for the standard out, which is cool, and that's helpful. All right, so there's our message that's getting displayed into the window. You can see how that's affecting it and changing it. And then we're going to do a break here, so that way, if it finds this particular event or whatever, it doesn't keep looking through the rest of the code to find something it's already found, if that makes sense. Basically, what we're saying here is we want to exit this whole switch statement, so we don't continue to hunt down to try to find what, if we're doing a key down or a key up, when we've already looked, which we've already executed the key up or key down. Does that make sense? So we don't want to continue to hunt for something we've already found and executed. It would make sense, because if we're sitting there trying to look, okay, for instance, say we'd have SDL key down, and that's done, right? So we activate it. It doesn't make sense to then check to see if SDL key down is this one here, or this one here, or this one here, or so on and so forth. It doesn't make any sense. So what we want to do is we just want it to quit right away. So that's ideal for us. And then I'll make us exit out of this loop and let us go ahead and quit altogether. Okay, so that takes care of our SDL mouse up all the way down. Let's look at our SDL mouse motion now. In this case here, so case SDL underscore mouse motion colon here. So if parentheses left mouse button pressed equals true, close parentheses, curly brace, and then we're going to say rotate x plus equals event dot motion dot yrel times 0.5 semicolon. Now why are we going to have the y-axis driving our x rotation? That doesn't make sense, right? No, actually it does. Let me show you real quick why it does. Okay, check it out. Our x-axis is going across horizontally, right, across the screen. And so if we rotate about that axis, that's not going to work for us, right? Because we rotate about the axis, that'll be literally up and down. But we want to rotate, side to side. So that axis that we rotate about would be the y-axis. So, in this way we're turning to the left or turning to the right about the y-axis, meaning that we're manipulating z and x positions here in order to rotate about the y-axis, which means we don't manipulate it on the y-axis. That's what the about means. So because of that, it's going to rotate left and right when we rotate along about the y-axis. It's going to rotate up and down when we rotate about the x-axis. So for this reason, we want our x position to drive our about y rotations, and we want our y-axis up and down to drive, for the mouse movement here, to drive our rotations about the x-axis. So that's exactly what we do here. So when the left mouse button is pressed, equals true here, I've set it up to where only when it's pressed, so that way it doesn't get in the way when you're trying to move the mouse around to do other things, like close the window, for instance. That would be really annoying otherwise. Open curly brace here, rotate x here, plus equals event.motion.yrel. So yrel, what's yrel? Well, yrel is relative y position for the mouse. There's absolute position and then there's relative position. In this case we want to use relative position because it's going to be relative to where we were last on the pixels. So it doesn't give like the actual position of where we are on the window. That's completely different. An example of absolute position would be this right here. Event.motion.x. Event dot motion dot y. So that'd be for your x and y. In this case, we don't want that. In this case, we want only relative position. So we want to see where we are according to where we were last, and not any other way. So that makes life easier for doing this motion, and it makes it for a nice smooth, easy manipulation, interpolation of our graphics as we maneuver our cursor here. So, for instance, if I, it's really smooth when I'm moving this back and forth. And same thing for zooming, comes out to be really smooth too. So that's nice. And it's because of that XY rel. If we did absolute position, it read in absolute position, 0, 0 would be the main here. So depending on where I move my cursor, it would do different things. Also, I couldn't have a negative value. That would be a problem. So, that's going to suck, because I want that negative value to sit there and drive it to go the other way. Otherwise I wouldn't be able to go left, or, and I wouldn't be able to go, down, as a for instance. That would suck. So, you definitely want your Y rel here and your X rel, because that's what's going to make sense. Okay, so I'm using it times 0.5 to take its value, which could be too significant, and I thought it spun it too fast. You can set your own value here if you like, but I like 0.5 because I found that really reduced the speed of the motion here by doing that. So by multiplying this times 0.5, it reduced the speed in half, actually. And then rotate about the Y here again. So we're going to rotate we're going to do this across the X relative motion here of the mouse, and I'm multiplying that times 0.5 also in order to slow it down because it's too fast too. So close curly brace there. If right mouse button pressed equals true, close parentheses, open curly brace. So we're seeing if, hey, was the right mouse button pressed? If that's the case, then we need to check something here. Alright, so only when the right mouse button is being held down will it zoom. Okay, so open greater than, open curly brace, zoom here minus equals event.motion.yrel times 0.1 semicolon. Why rel? Because that'd be up and down. So that makes sense for zooming in and out. And why minus equals when this is plus equals? Well, if you think about it, remember we did negative 5.0 in order to place our cube 5 units back, right? Cool. And that's awesome, but you have to realize that that's going to mean that we need to have our zoom be negative equals, because that way when we move our mouse up, it's going to zoom out, and then when we move it down, it's going to zoom in. So, other way around. Hold on. Alright, let me show you. If I move it up, it's going to zoom in, which makes sense. Because when I move my mouse cursor up, you expect it to zoom in. And then when I move my mouse cursor down, it's going to zoom out. So if we want to zoom in, we have to do negative value there. Subtract equals there. And if we want to zoom out, then of course we just need to go down with the value there. And that just worked out right for us. If you want to set yours up differently, you can. I also found this to be really fast for the zoom. Way too fast. So if you find the zoom to be still too fast for you, you can make this value even smaller here. So, but anyways, I multiplied it times 0.1, and this really slowed down how fast it zooms in or out. It was getting ridiculous to how quickly it would zoom, to the point where you couldn't hardly control it, I thought. So I reduced it, and I got smoother, cleaner animation, and it just didn't like suddenly jump all over the place when I was trying to zoom. So, it made it more manageable, but also feels very fast and efficient at this speed here. Basically, this controls our speed. You can even set special variables for this if you so desire to control these values, which is nice. And this is great for, especially if you're going like a interface for the end user. For instance, the game player. That person may want to set the speed at which their mouse moves stuff. This is typical. A lot of people want to do this, and that's something a lot of programmers allow in their user preferences. So this is how you could do it, and you could just set a variable for that, and then make that variable accessible within the menu. And then once one changes that value, it changes the speed here for these values here, and that works out really nice. I've commented this out because if I don't, it'll eat up tons of space. But this is for debugging purposes. so that you can see what's going on. And if you would like to see all this code in action, then by all means just uncomment it. But here we have fprintf here, open parentheses, std out for standard out file, comma, quotes, mouse moved by %d, comma, %d, space 2, open parentheses, %d, comma, %d, close parentheses, /n, close quotes here, semicolon, comma, event.motion.xrel, comma, event.motion.yrel, comma, event.motion.x, and event.motion.y. Okay, so we're saying it's moved by this relative value, and then this is its absolute actual value inside the window here. And that's what's going on here is our relative values here, and then here's our absolute position values on the screen. Of course, it's close parentheses, semicolon, and I've just finished commenting it out here with my comment from multi-line comment here from C++. Then I'm going to do my break statement in order to kick out of this thing if this was what we were looking for. Case here, SDL underscore mouse button down. So if someone hits the mouse button down, if open parentheses event.button.button equals 1, which is going to be left button, of course, close parentheses, left mouse button pressed equals true, semicolon. Now if you want for this one, you could have set this up with a constant or something like that so that it's more human readable than just a value here. It's better programming if you do that, but I didn't bother. If here open parentheses event.button.button equals 3, close parentheses, that's going to be your right mouse button, so right mouse button pressed equals true, semicolon. I kind of was piggybacking on the idea that, hey, they see it right here, right mouse button pressed, so they know that 3 has to be the right mouse button. But maybe I'm being a little too thinking that people will just figure that out automatically. Should probably really honestly comment it over here to the side, or actually put in a constant value there, constant variable. Fprintf here, open parentheses, std out, comma, in quotes, mouse button %d pressed at, open parentheses, %d, comma, %d, close parentheses, /n here, close quotes, event.button.button, comma, event.button.x, comma, event.button.y, close parentheses, semicolon. So this is our absolute value here for when the mouse button is being pressed down, where that mouse is appearing. And then we go to our, and then we break, of course, for that one. Then we go to our final one, which is our case, SDL underscore quit, colon, done equals true. So if we have an SDL quit event occur, then we're going to go ahead and quit the loop and quit the program. Break, semicolon, not really needed, but put it in there anyways because I felt like it. Close curly brace, the reason why it's not needed is because we're at the very end of the whole case statement, so there's nothing to break out of. Close curly brace here. And for the switch statement anyways. So when we're breaking out of this switch statement here each time we find what we're looking for, so that way we optimize it more for our code. Now mind you, we continue the loop for each event here through all the events in the event list. So we're going to keep doing this every single frame here. So we're going to loop through all the events in the actual event list each time. So that's why when we find the particular one we're looking for, we want to get out of it because we need to find the next one that we're looking for to do said action for that particular event. So that makes sense. Close curly brace here to close out our loop. Well, yeah, the polling event loop, not our game loop. Our game loop is still out here. So I'm going to do my keyboard direct access here outside of the event loop here. I wouldn't want to do it inside of the event loop. I would want to do it outside of it. So that's key, and that's very important. It wouldn't make sense to do that inside of the polling event. Otherwise, you're going to have your direct access keyboard function getting executed far too many times. It should only be getting executed once every frame, and not for every little action that occurs during that frame. Because otherwise you're going to be executing this function many more times than what you ever dreamed or needed to do. So again, we only want to actually detect our keyboard access per frame. Otherwise, what does it matter if we sit there and read in that someone did, held down the over key or whatever, multiple times during a single frame, it doesn't matter. It's still going to be over to the side, your arrow key to the left or whatever. It doesn't matter. And then you would have to sit there and take in all that input for that frame and then try to figure out what the overall accumulated key presses would be for that. It doesn't make sense to do that. Really, you can only react to and display the results on the screen once every frame for what the input is. So essentially, really, honestly, just reacting to whatever key input is per frame is the only thing that really makes sense, because if you do it more than that, then you're trying to react to something. You can't possibly display the results of what they're pressing in time, so it would be pointless. On the other hand, it doesn't make sense to sit there and take in key input less than once per frame, because otherwise then your actions might be jerky because it's not reacting per frame. It needs to be updating per frame for whatever someone's hitting on the keys, so that way the game looks responsive. Otherwise the game's going to become halted, jerky, unresponsive, etc. So we need to do it just once per frame, basically, for the most optimized setup here. Close curly brace here. And then SDL_quit in order to quit SDL. Close parentheses, semicolon, and then return 0 to let us know that, hey, we had successful execution of our program and there were no errors. So return 0, semicolon here, close curly brace. Alright. And that's the entire program. And once you have that all in there, now you can hit your build execute button there inside of code blocks, and have fun playing with your mouse. Zoom in and out, rotate with your keyboard here. Pretty cool. And there's all kinds of stuff you can do. Later on, we'll get into how to do game controller programming and how to do direct access for the mouse too. And don't forget this keyboard function actually called up to this direct keyboard access here. Yeah, so this is our direct keyboard access here. But we'll get into how to do that with the mouse in the next video set, along with also the joystick and the keyboard too. Okay? And beyond that, we'll get into how to do it for all the keys on the keyboard, not just a few. So with that, my name is Nate Nestler. This is for Hyperactive Studios, and this was SDL and OpenGL programming. Thank you very much.